Hello everyone, welcome back to the channel. Today we are solving LeetCode problem 955, delete columns to make sorted 2. You are given an array of n strings called strs, and all of these strings have the same length. You are allowed to choose any set of column indices and delete those columns from every string. After deleting the selected columns, the remaining characters in each string stay in their original order. For example, if the strings are A, B, C, D, E, F, and U, V, W, X, Y, Z, and we delete columns at indices 0, 2, and 3, the final strings become B, E, F, and V, Y, Z. Now here is the goal. We want to choose the deletion indices in such a way that after deletions, the array of strings is in lexicographic order. That means strs0 is less than or equal to strs1. strs1 is less than or equal to strs2, and so on. Your task is to return the minimum number of columns that need to be deleted to make this possible. This problem is about carefully comparing strings column by column and deciding which columns must be removed to preserve lexicographic order. Next, we will look at examples to see how this works step by step. Now let us go through the examples to understand the problem better. Example 1. The input strings are CA, BB, AC. Initially, these strings are not in lexicographic order. If we delete the first column, the strings become A, B, C. Now the array is in lexicographic order from top to bottom. We need at least one column deletion to achieve this, so the answer for this example is 1. Example 2. The input strings are X, C, Y, B, Z. These strings are already in lexicographic order, as they are. Even though the characters inside each string are not sorted, that does not matter for this problem. Since no deletions are required, the answer is 0. Example 3. The input strings are ZYX, WVU, TSR. No matter which columns we keep, the strings will never become lexicographically ordered. So the only solution is to delete all columns. That means we delete 3 columns, and the final answer is 3. These examples show that in this version of the problem, we must carefully decide which columns to remove so that the overall order of the strings is preserved. Now let us walk through the solution and understand how this greedy approach works step by step. This solution directly implements the strategy we discussed earlier, processing columns from left to right and resolving row order gradually. First, we store some basic values. We store n as the number of strings, and m is the length of each string. This helps us loop through rows and columns easily. Next, we create an array called resolved. This array has length n-1. Each index I represents whether the order between row I and row I+1 has already been decided. Initially, all values are false, meaning no row order is decided yet. We also keep a count called unresolved, which tracks how many row pairs are still unresolved. At the start, all row pairs are unresolved. We also initialize a variable deletions to 0. This will store the number of columns we delete. Now we start scanning columns from left to right. For each column, the first thing we check is whether all row pairs are already resolved. If unresolved becomes 0, it means the overall order is already fixed, so we can stop early. Next, we check whether the current column is bad. A column is bad if for any unresolved row pair, the upper row character is greater than the lower row character. That would violate lexicographic order. So we loop through all unresolved pairs, and if we find even one violation, we mark the column as bad. If the column is bad, we must delete it. So we increment deletions and move on to the next column. No further processing is needed for this column. If the column is not bad, that means it is safe to keep. Now we use this column to resolve row order. For every unresolved row pair, if the character in the upper row is strictly I, smaller than the character in the lower row, then the order between these two rows is now fixed. We mark that pair as resolved and reduce the unresolved count. This is the greedy part of the solution. Once a row pair is resolved, we never compare it again in future columns. This is correct because lexicographic order is decided at the first differing position. We repeat this process for each column until all columns are processed, or until all row pairs are resolved. At the end, the value stored in deletions is the minimum number of columns that must be removed. So we return deletions as the final answer. Why this solution works. We only delete a column when we are forced to. We lock row order as early as possible, and we avoid unnecessary comparisons. Time complexity is rows times columns. Space complexity is linear in the number of rows. This is a classic greedy problem, and once you understand the lexicographic insight, the implementation becomes very clean. Next, we can run this code, submit it, and confirm it passes all test cases. All right, now that the solution is fully in place, let us go ahead and run the code. Nice. All the test cases pass successfully. That means our greedy logic is working exactly as expected. Now let us hit submit. And there we go. Accepted, all test cases passed. That brings us to the end of this problem. If this explanation helped you understand delete columns to make sorted too, make sure to like the video, subscribe to the channel for more daily LeetCode walkthroughs, and I will see you in the next challenge. Happy coding! All right, now that the solution is fully in place, let us go ahead and run the code. Nice, all the test cases passed successfully. That means our greedy logic is working exactly as expected. Now let us hit submit. And there we go. Accepted. All test cases passed. That brings us to the end of this problem. If this explanation helped you understand delete columns to make sorted too, make sure to like the video, subscribe to the channel for more daily LeetCode walkthroughs, and I will see you in the next challenge. Happy coding!